Okay, first thing I wanted to show you is where to find those arrow pushing videos. All right, so if you go into the course, go to module exam 3, okay, and then scroll down to this required video pushing arrows. So I've got 2 videos there, and I've got these notes for the arrow pushing video. So if you have a copy of those notes, which see, did I give you? You did. Yeah, there's a copy right there in between the 2. Yeah, have that with you when you're watching the video, because it kind of follows along with the video with the stuff that you ought to be watching for. Now, a word of caution. Dr. David Van Branken, who does these videos, is only half bad. He's a David, so he's half good. But he's doing the videos for chemistry majors. So they're going to be really, really deep and involved. All right. So what I want you to do is to focus on what the arrow represents, how to use it in a mechanism, and what are forbidden uses, right? And then try to get something in terms of the mechanism, like what an arrow means. We're going to talk about that in the upcoming slide set. But I don't expect you to be an expert on arrow pushing per these videos. I just want you to be able to use the arrow pushing technique to help you with mechanisms. Okay. So that's why I created those notes also. Okay, you've got till next Monday to watch those videos, and then we're going to have a quiz on Monday on arrow pushing. Let's see. Okay, so
sorry to interrupt, but in our homework, would that be considered like an inner chapter?
I don't think there's an arrow pushing inner chapter.
Okay.
No, the inner chapters.
I think we just have C and D left.
Yes, C and D. D is naming compounds again. Let's see, what is C? C is, where is C? Oh, here's C. Molecular orbital theory and chemical reactions.
Okay, so we don't have a homework on arrow pushing then?
No, there's no
Okay.
There's no homework chapter on arrow pushing. Dr. Carty embeds arrow pushing into the chapter we're coming up with, and then uses it in subsequent chapters. And while that's okay, I think we need a focus on arrow pushing before you even start using it.
Yeah.
Yeah. And that's why I called on Dr. Van Branken. In fact, the first time I taught this course, I sent him several emails saying, "What do you mean by that?" And he responded.
Yeah.
I was surprised. Okay. So let me stop that share and share the, let's see, to pin that one and share. I think it's this one. Yeah. There we go. Now I'll make a slideshow out of it. All right. Let's go back to the top. All right. So chapter 6 is starting to introduce the concept of reaction mechanisms. I don't know if you remember from your general chemistry courses. Let's see. I'm trying to think when we get into mechanisms. In general chemistry. Hold on a second. Since you're in my other course, I want to see if We're in that right now, aren't we?
No,
Yeah,
we're,
kinetics.
yeah.
Yeah, kinetics introduces the idea of mechanisms. Okay, so mechanisms carry over into organic chemistry too. And a mechanism is simply a step in an overall reaction. So most reactions require at least two elementary steps, we call them, to complete the overall reaction. So do you guys remember that from general chemistry? No.
Say it one more time.
Well, let's see. You probably got it when you were talking about kinetics, reaction rates. When you talk about reaction rates, if you have an overall reaction, then you you can break that reaction down into individual steps, and those steps have their own rates.
Like
One
rate
step,
law stuff?
yeah, rate law.
Okay.
Mhm.
Yes.
So the individual steps of the mechanism will usually have different rates, and the slowest elementary step is the bottleneck. That's the one that determines the overall rate of the reaction. Okay, that's where I'm jumping off from kinetics into organic. Okay, so from now on, we're going to take reactions and approach them from a mechanistic standpoint. In other words, individual elementary steps go into a particular overall reaction. Right? The overall reaction you can do experimentally and say, all right, I put these two reactants together and I get these two products. That's overall. What happens in between? What happens in here in the arrow? Right? It goes maybe an elementary step here and then another elementary step there to get the overall. Okay. And that's where arrow pushing should help, because it informs your assumptions about what elementary steps are involved in an overall reaction. And the first one we're going to encounter is proton transfer. Proton transfers are very common. So we're going to start there, and they're very simple too. All right. So this beginning part is review for mechanisms. The mechanism shows you the elementary steps and how the reaction takes place in those stepwise procedures. And hopefully also informs you as to how the reaction takes place. I mean, rather than, in kinetics, when we study kinetics in general chemistry, you can propose different mechanisms. Like this mechanism might have 3 steps. This mechanism might have 6 steps. And you just go in and you propose whatever mechanisms you want, and then you weed them out. Say this one can't be because, this one can't be because. And eventually you get down to one that's the only one that makes sense. It's kind of like Sherlock Holmes, right? Ultimately these mechanisms also can make predictions about the reaction. So if you look at the reaction in terms of what are the reactants, and then what is the most likely mechanism, then you may even be able to predict the outcome. What are the possible products? And that's useful if you're trying to synthesize a new compound, especially in terms of organic chemistry, because that's what they do all the time. Most of them, they synthesize compounds. Okay, so that's why the textbook is named what it is: Principles and Mechanisms. So Carty is heavy into mechanisms, because he believes that they simplify organic chemistry. It's easier to understand rather than memorizing this named reaction and that named reaction and this named reaction. Just rote memory, and if you encounter something that's a little bit different, what do? If you approach it from a mechanistic standpoint, then you might be able to solve the problem. And there are a few common elementary steps that we're going to cover before we finish the course. This is the first of those, the proton transfer. Most reactions have one or more combination of these elementary steps that we're going to study. So it's not like we're shooting for the moon. We do have some, we have some cards to play. All right. So remember the definition of a Bronsted-Lowry acid and base. Okay. So you have your acid here, reaction with a base. Now, if I use the I'm having trouble in my memory. Shoot. I'll think of it in a minute. But if we write our base that way, then we know the outcome. Right? We should expect a salt plus water, correct? But if we have simply an acid in water, right, then this is the acid and water becomes the base, right? Water can be an acid or a base. It's amphoteric. So if it's the base, that means it accepts the proton. So we end up with this plus our hydronium ion. So this is acid base. This is the conjugate base of acid, and this is the conjugate acid of the base. Okay.
When you talk about H2O being like an acid or a base, like, you know, like when water is alkalized, is that like the same thing?
Right. If you add base to water, then the water becomes the acid. It donates the proton to the base. Right.
So
if you acidify it, then you're doing this. If you alkalize it, then you're doing, actually you're doing this. Say the base plus water transfers a proton to that base, and it makes the conjugate acid of the base plus hydroxyl.
okay.
Okay. Almost had it. Okay, so that's just a review. And if we put in all of the lone pairs, then one possibility is now what Carty has done here is he's made this one a spectator. Right? So that means you can ignore that one and you only have the acid and the hydroxyl to deal with right here. Okay, that's what he's done. This is the hydroxide ion, and the hydroxide ion is an extremely powerful base. It loves hydrogen ions. It is probably, I don't know too many bases that are stronger.
And where's that one?
This is the hydroxide ion.
And it's the strongest.
It's yeah. Until you're told otherwise, it'll be the strongest base in any reaction. Okay. So we're treating B as a spectator. That means since we're not going to have B over here and we're not going to have B over here, then we have that one, and the proton is transferred to that hydroxyl. Okay. Now, what happens in this process? If we draw it like this, let me erase this because I need the room. If we draw it like this, where we have a covalent bond with the hydrogen ion, with the hydrogen, then in order to transfer that proton, we have to break that bond. Okay. And when we break that bond, protons, I tell my class this in general chemistry too, protons never exist free floating in a reaction mixture or a solution. Never. They're always transferred. Now we write them as if they were free floating for convenience, but that's not what happens in the reaction. this proton's got to go somewhere. It can't just come out here and float around as a free proton. They don't do that. They transfer. So this proton is going to transfer and just break that bond and form a bond with this one. That gives us water. Right? That gives us this. So this new bond is formed when that proton is transferred to this base. Well, what happens is the, let's see, I think the next slide, we're starting to introduce the concept of the arrow notation, arrow pushing. Sometimes they call them curved arrows or curly arrows. The curly arrow always tracks the movement of electrons. And in the beginning, we're going to start with a double barbed arrow. A double barbed arrow means two electrons move. And they're always valence electrons. We never move core electrons, ever. They're always valence electrons. So they'll either be lone pairs moving, or they'll be electrons from a bond. In this case, we've got lone pairs here that are moving, and this lone pair moves over here and connects with that hydrogen. Okay? Now, in order to break that bond, those electrons have to go somewhere too. Right? So in this case, both of them go to that atom. Right? So we moved electrons over here. So when you move those lone pairs over here to that atom, you're actually forming a bond. So this is that bond right there.
So would it cancel out the A's?
Cancel out what?
Like the A's? Like up top, like where you have like H-A and then plus, and then you have like,
Well,
do those cancel out? Yeah.
when you break that bond,
Yeah.
now both of those electrons go to this A.
Yeah.
And since one electron was already assigned to A, then you add another electron, gives you a negative charge.
Oh, okay. Yeah.
Okay.
I get what you mean. Okay.
Yeah. So, if you were calculating formal charge,
Yeah.
like if calculating formal charge for that, you'd already have used one of those electrons for the formal charge. But if both of them are being transferred over, that extra electron gives you the negative. And that makes this hydrogen available to bond with that oxygen using this pair, lone pair of electrons. And that's this lone pair ends up right there in that bond. Okay. So what we've done here is we've pushed electrons from an electron-rich source, right? Electron-rich to an electron-poor source. Like this is going to be poor because this is more electronegative than hydrogen. Virtually anything is. And that means it's pulling on those electrons anyhow. So it's depleting this one to where it's slightly positive and this one's slightly negative, especially if we use the example there, hydrogen chloride or hydrochloric acid, which is a strong acid. That means that we're like this. Okay. So that's the way arrow pushing usually goes, from electron rich to electron poor. All right. So there are some rules. Now the videos, Van Branken's videos are going to elaborate on these rules. Okay. He's actually going to tell you how many of these arrows you can have in one mechanism. I think the limit is 3. Right? If you go past 3, then you got a pretty poor mechanism. Right? Okay. Let's see if Cardi gives us any more information here. Yeah, curved arrows originate from either a bond or a lone pair. So we originated here from a lone pair and went to an atom. And here we originated from the bond and went to an atom. If the lone pair goes to an atom, you're forming a bond. Right? So this arrow says the electrons are going this way, but they're going that way so we can form a bond with that one. And in the process, you have to break this bond. So those electrons have to go somewhere. So those electrons go to this atom. But they're the result of a broken bond. Okay. Now, when we have competition between an acid and a base, we want to focus on the pKa. Remember what the pKa is?
What is it?
Oh, we haven't got there yet, have we?
Well, it's part of K. It's like a branch off of Ka.
Right. Ka is the equilibrium constant for the acid dissociation. Right. So if we have, I'm going to give you a head start on the acid-base chapters.
I was thinking about the protein deficiency disease, the pKa, or
That's different.
yeah, that's what I was thinking of when you said pKa. That's what my mind immediately went to.
So if we have, let me give you a quick tutorial. Now I'm going to use a notation.
Because our professor taught us in some crazy way and on how like calculate pH, pKa,
Uh-huh.
all of that.
Uh-huh.
And then like the concentration of hydronium and hydroxide and all of that. And then I learned how to do it in the easiest way and never got a question wrong. That was the easiest exam I took again.
Okay.
So if they're having to do it in some crazy way, don't do it. I'll show you.
I try to make it easy.
Yeah.
So
I'm just saying.
if you have an acid, I'm going to write this simple. Rather than transfer the proton to a water molecule, we're going to simplify it, and we're going to break physical rules. So when we say it's dissociating, we're producing that and that. Right? We know that's not the way it happens. But the Ka, or the equilibrium constant, right now, and this is new, we haven't got to equilibrium yet in our Chem class. The equilibrium constant is the concentration of that times the concentration of that. That's what the square brackets mean. In molarity, divided by the concentration of that. So the reactants go in the bottom, the products go in the top. That's the Ka. Okay. Now, if we measure a certain concentration of H plus in solution, right? You could talk about the reaction in terms of that, but it's simpler to use Sorensen's transformation and say, we're going to take the log of the hydrogen ion concentration. And that would be, give you, rather than like 1.5 times 10 to the minus 7, it simplifies it into a single number, but it also makes it negative. Right? So that's why Sorensen put a negative in front. So negative log of hydrogen ion concentration is pH. Little p, big H. Okay. You can do that same transfer. That's simply a math formula. You can do this same transformation if you have the K. And that gives you pKa. Okay.
So it's different than natural log. It's just regular log.
Yeah, common log.
Okay.
Yeah. We use common log because all of these concentrations are powers of 10.
Oh.
That makes it simpler.
Yeah.
Okay, so when we say pKa, if the Ka is big, what does that mean? Well, if the Ka is big, that means products are favored. That means more hydrogen ions are favored. Right? So the larger K means more acidic. But if we do the transformation, the log transformation with a negative sign makes the pKa small. So the smaller the pKa, the stronger the acid. Just like the smaller the pH, the more acidic the solution. Okay. So when you're comparing pKa's, the smaller pKa is the more acidic acid. And that's where I'll get back to now, competition between acid-base reaction and a conjugate acid conjugate base reaction. So in order to, let's see, you still writing?
I'm done now.
Okay. So if we have this acid-base reaction and we've left out the spectator ions, so now we have the base. And the base, since we don't know what the base is, we're just going to say it's got at least one lone pair, and it's probably negative charge because it lost a hydrogen. Then we're going to react it with an acid, right? And it's going to yield, actually, go both directions. It's going to yield this HB, the conjugate acid. This is the base. This is the acid. This is the conjugate acid of the base. And this one is the conjugate base of the acid. Okay. I think for clarity, Cardi circled these like that. So I'll do the same thing. Okay. So how strong is that acid? It's related to its pKa. The pKa of that one. How strong is this acid? It also has a pKa. Right? So if this one has a very, very, very low pKa, it's a strong acid and it wants to go this way. So it's competing with a driving force to go that direction. If this one has a much larger pKa, its driving force to go this way is not as strong. So the competition is that if this is smaller than that one, it's more acidic, favors products in this reaction. That's where we're comparing the pKa's of the two acids. And there's in chapter 6, there's a table 6.1 that gives you pKa's for a lot of the organic acids that we're going to encounter. All right.
So would that mean pKa 1 is stronger than pKa 3?
Stronger than, but it's also smaller than.
Okay.
Because the way the transformation, the negative log transformation makes the bigger Ka, now the smaller pKa. Okay. They go in opposite directions.
Yeah. Okay.
So yeah, some of these pKa's can be negative values, negative 15, negative 20.
So if you were to have like a negative 10 compared to a positive 2,
Yeah.
which would be stronger?
The negative 10, yes.
Okay. So the lower the number, the stronger.
Right.
Okay. But the lower the number, the smaller it is.
Well, it's smaller relative to the other one.
Okay.
Right? Because you can go small in the positive realm, like from 10, 9, 8, 7, 6, 1, and then you can go 0, negative 1, negative 2. You're still getting smaller.
Yeah. Okay. Okay, I understand.
Okay. All right. So we already covered that statement. The lower pKa is a stronger acid. Remember that each difference in the pKa, because it's a log transformation, each difference is a factor of 10. Right? That's the way logs work. So if you're comparing a pKa of 2 for one acid versus 10 for the other acid, the difference between the two is 8, or 8 decimal points. 2, 3, 4, 5, 6, 7, 8. Right, 100 million times stronger than this one. Okay. And the example that they're giving, that Carty gives here, is a comparison of ethane versus trifluoromethane sulfonic acid. Right? The TMS is -13 and the ethane is 50. And the difference between the two is 63. 10 to the 63rd power is the difference in strength. That's a pretty wide gap. So if you put those two together in solution, the TMS is going to win. It's going to dissociate and produce a lot of hydrogen ions. And what effectively that does is the stronger acid loses those protons, and they got to go somewhere. So they go attached to the base, and they form the conjugate acid of the base. And that is, in some terminology, you would say the base is fully protonated. You're forcing protons onto it. That makes a whole lot more sense when we start talking about actual biomolecules like amino acids. Okay. So in this example, we've got a hydroxyl with, which is, I don't even think we have a pKa for the hydroxyl because it's not going to give up that proton. So the hydroxyls, you can be pretty sure that any acid they encounter, they're going to take a proton. In this case, hydrochloric acid, yeah, it's going to give up that proton, no problem. The pKa of water molecule is 14. Oh, by the way, while we're on the subject, how would we do the pKa of a water molecule? It would dissociate into that plus that, correct?
Yes.
Yeah. Okay, so the Ka would be equal to H plus and OH minus.
And then put it over H2O.
That's the temptation. But by convention, pure liquids and solids are eliminated from the expression. Why? Because they don't change concentration.
So it's just that.
Yeah, that's it.
Okay.
So the Ka for water is 1 times 10 to the minus 14. And the negative log of that Ka is just the 14. That's where the pKa comes from. For water. That's why, if you've heard of pH 7 is neutral, that's when the hydrogen ions and the hydroxyl ions are exactly equal in concentration. And if this is the case, the only way you can get to that value is if this is 10 to the minus 7 and that's 10 to the minus 7. So the negative log of 10 to the minus 7 is pH 7. That's where that comes from. Okay. So the top example there has the hydroxyl actually, that hydroxyl is going to want the proton, right? So we can draw those curved arrows as is on the bottom for that ammonia molecule. But the pKa of ammonia is 36. All right, let's see if that's, did they get that up here? 36. Yeah, ammonia is 36. But the pKa of water is 14, which means water is a stronger acid than ammonia is. So the competition in that reaction, when you have a hydroxyl, a strong base, along with ammonia, it's going to favor the production of, it's going to favor the left-hand side of the reaction. Because the competition goes to the one with the smaller pK. And water has a smaller pK than ammonia. So the left-hand side of the reaction is going to be preferred. All right, so predict which side of the reaction is favored to what extent. All right. So what do we have? The first one. That molecule is acetic acid, or IUPAC name would be ethanoic acid. So acetic acid has a pKa of, here it is, I'm close, 4.75. Right, so the first one is 4.75 for ethanoic acid. And what's the conjugate acid on the right-hand side? All right, that's CH3 and H2. That's methylamine. So let's find that one. I think I found it. Yeah, methyl ammonium ion. So that methyl ammonium ion on the right, how do I know that that's the conjugate? That's the acid we're looking at? Because, I'm sorry? Well, I know to look for the pKa of that far right group because it comes from the left-hand side, which actually accepted the proton. So that's the base on the left-hand side. That methylamine is the base. But the methyl ammonium ion on the right-hand side is the conjugate acid. That's how I know that I need to look for the pKa for that one. And the pKa for that one is 10.63. Okay, so it's a competition between these two. Which direction is the reaction going to go? To the right, right? This one donates.
But maybe that's different.
No, you go, okay, think of it this way. If this is a stronger acid than that one, this one's pumping more protons into the environment. Yeah,
Okay.
right. Okay, so let's see what Cardi has to say about it. The acetic acid, what's the acid on the reactant side, on the product side? Okay, acetic acid on the reactant side, methyl ammonium on the right-hand side. Then we compare the pKa's 4.75 and 10.63. Okay. The lower value, 4.75, is the stronger acid, which means that the stronger acid has a greater tendency to donate protons, which drives the reaction toward the products. The difference between the pKa's is 5.88. So, the acid on the reactant side is 10 to the 5.88 times stronger than the one on the product side. Now, how does that answer the question? Right. To what extent? Okay. So Cardi is using the difference between the two as a power of 10. So we would subtract this one. That's the difference. And this is the extent of the difference, 10 to the 5.88, which is 7.6 times 10 to the 5th. So that gives you an idea that the reaction is driven to the right to an enormous extent, 10 to the 5th power. All right. I'd like to wait till Katie gets back because we haven't covered. She's taken my second semester general chemistry right now also, and we haven't got to acids and bases yet.
Yeah, that would be tough. It was tricky until it clicked and then it just made sense. Like, it took some practice.
Mm-hmm.
I mean, this was a lot of words. The conjugate acid of the parent and the like just all of that stuff. That was just so crazy.
So where did you take that course?
WVU. I've taken all my general chemistry at WVU.
Okay,
We took 110, which was, I mean, my high school chemistry was terrible. So I took 110, which is very.
Introductory?
Yeah, I mean,
Okay.
like you were like, what is the periodic table? Like,
Okay.
It was great. And then
Okay.
115, which was kind of like general chemistry 1, and then
Okay.
116, was general chemistry 2.
Do they separate their labs in different course
We have
name?
like, yeah, we have like a 3-hour lab each. And so it's like, you learn a lot.
Oh. So that lab probably has maybe a section of time set aside for lecture too, doesn't it?
Yeah. So
Then
we
you
have,
go in the
like,
lab.
like 1 hour of lecture, Monday, Wednesday, Friday. And then we have lab for 3.5 hours once a week. So
Okay.
it's like,
Okay. I had an organic course that I took from 5 o'clock to 10 o'clock in the evening. And we went in from 5 to 6 for a lecture introduction to the material. And then from 6 to 10, we did the labs. So by the time I left, the doors were locked, and once you go out, you can't get back in. Okay, now that you're back, when you have a strong acid, like hydrochloric acid, right, and it dissociates and produces the conjugate base. Right? So this is the acid, there's the conjugate base. The strength is inverse. So that if the acid is strong, the conjugate base is weak. And what we mean by that is strong acids want to give up protons. Weak bases don't want the protons back. That's the way I look at it. So once this guy gets rid of his proton, he doesn't want it back. Right? If this is a weak acid, then it produces strong conjugate base. Right? It doesn't want to give up its proton, but when the ones that do, the very few that do, are very strong bases. They want protons wherever they can get them. Okay, that's the trend. So our example here is a negative hydrogen ion versus a negative acetate ion, not an acetate, acetylene. So if the pKa of H2 is 35 and the pKa of acetylene is 25. So the acetylene is a stronger acid, right, than hydrogen. So that means the ion that's formed from acetylene is a weaker base. So that means the H minus is a stronger base than the C minus. Okay, you just flip it. All right, let's see what he means by leveling effect. This is characteristic of organic reactions. When you're trying to carry out a particular reaction, you may not want the solvent to react with anything in your mixture. You just want it to serve as a matrix to put everything in solution so that they can interact with each other. That's why a lot of organic reactions are done in non-aqueous environments because water is so reactive. Now, sometimes you do want the water to be a reactant. In that case, you have to consider it in your mechanism. Okay. So that's where the concept of protic versus aprotic solvents comes in. The protic solvents have a hydrogen available to donate. So they get involved in the reaction. There's a potential for that. The aprotic solvents don't have protons available to donate. So, what happens is if you have a solvent that is active in the reaction, it's part of the mechanism, then what it does is it produces an undesirable side reaction, either a proton acceptance or a proton donation. And that proton side reaction is not desirable. That's what he's calling a leveling effect. So the strongest acid that can exist in solution at any appreciable concentration is the protonated solvent. If the solvent is protonated, then it has available that proton for the reaction. And the strongest base that can exist in the solution is the deprotonated solvent. So what do they mean by that? If you have an aqueous solution, then this would be the protonated solvent, and this would be the deprotonated solvent. And depending on the reaction, this can donate a proton to something, or this can accept a proton from something. All right. So here's our example with water. If you can't have an acid that's stronger than the hydronium ion, or a base that's stronger than the hydroxyl ion in any appreciable amount. If we look at the water reacting with HCl, it'll produce a hydronium ion and a free chloride ion. If we look at the dimethylamine ion, and if it reacts with water, then it becomes protonated and produces the dimethyl amino compound versus the hydroxyl. Now, which one is favored? Well, if you've got a strong acid reacting with water, the product is going to be favored. It's going to favor the chloride ion and the hydronium ion. If you've got a base that's stronger than water, then you're going to form the protonated reactant. There must be more to this story. Okay, so what he's getting at is choose your solvents wisely. So if we want to carry out a reaction involving HCl or that anion as a reactant, then water is a poor choice for the solvent. Because what does it do? It takes a proton off the HCl, and you want the HCl in there to react as itself. Or you want that anion to react as itself, but if you've got a water in there, it's going to protonate it. And now it's not available for reaction. Okay, so water would be an unsuitable solvent for either one of those. So the overall rule then would be a solvent is unsuitable for a particular reactant R, if the R is stronger acid than the solvent, conjugate acid. So the conjugate acid of the solvent would be, if it were aqueous, the conjugate acid would be the hydronium ion. So you look at what is the pKa of the hydronium versus the pKa of your R. So if the R is stronger than that one, then it's unsuitable. Let's go back. Well, no, that's right. We need to go forward because we're not talking about R's in that previous slide. That doesn't help at all. If R is a stronger base than the solvent, conjugate base, then it's also unsuitable. So you compare the reactant in your solvent to the pKa of the conjugate acid of the solvent. Or you compare the R to the base strength in your solvent. So if R has a higher pKa than the solvent, then it's unsuitable. All right, let's take this example. All right, there's our dimethylamine anion, and there's diethyl ether. And we got those. Oh, is the diethyl ether suitable as a solvent for this according to the leveling effect? All right. So is that anion a stronger base than the conjugate base of the diethyl ether? Let's see, what's the diethyl ether? pKa. Diethyl ether pKa is 45. That's diethyl ether. pKa is 45. It's a very, very, very weak acid, which means it would be an extremely strong base. How about the dimethylamine ion? See if I can find it. Dimethylamine. Okay. N-methylamine or dimethylamine. The conjugate base. All right. The pKa is 38 for this one. Right there. So the conjugate base, let's see. Trying to remember how to calculate the pKb for that would be, right? Well, we can compare these acids, right? This is the pKa for the acid, this is the pKa for the base, which means what? This is a stronger acid than this one, which means the stronger acid produces a weaker base. So this is the weaker conjugate base, would be this one. Okay, that's the weaker base. So the question is that a stronger base than the conjugate base of this one? Well, no. It's a weaker base. Okay. So the potential undesired proton transfer reaction would be, this is a weaker base, right? So it's not going to take a proton from that. It should not interfere. The stronger acid is on the product side. So this reaction will not be favored. Therefore, this ion will not be consumed by a reaction with the solvent when it's dissolved. It remain predominantly that value, meaning the solvent would be suitable. So we're saying this solvent is suitable because we want this as part of our reactant, right? And it's not going to be consumed. It's a weaker base. It's a weaker conjugate base than the conjugate base over here. So that means it will not attract a proton from this. Okay, does that make sense? Yeah, I know. It's a poor description. let's move on to equilibrium. Maybe it'll make more sense later. Okay, equilibrium. We haven't got to equilibrium yet, but we just finished kinetics. So the next chapter we get into is equilibrium. And equilibrium is founded on kinetics, reaction rates. So when you have a reaction that's going from reactants to products, it can also go from products to reactants. And each one has a rate, right? A rate equation, like a K for that one and a K for this one. Okay. So this one can go at a certain rate. This one goes at a certain rate. When the concentrations change to the point where the forward reaction rate and the reverse reaction rate are balanced, that's equilibrium. All right, so ethanoic or acetic acid can exist in water because it's a weaker acid than H3O. Yeah. So the protonated version of acetic acid is favored. And they are in equilibrium. And if we write the equilibrium expression, we come out with a pKa of 4.75. Right, so it's slightly acidic, but it's not extremely acidic. Right, anything less than 7 is acidic. So that's why you can we use vinegar to acidify our salads. Or use any kind of organic acid, like I don't know, lemon juice. Like they're acidic, but they're not strongly acidic. Although we used to keep bottles of glacial acetic acid in our cabinets. That's 100% acetic acid. Now, it's dangerous.
What would you use it for?
Oh, you dilute it for different reactions. If you start off at 100%, then you can dilute it to any concentration. But if you start off with vinegar, you have to start off at 5% and go down from there. But if you need more stronger acetic acid, then you have to go to glacial and make it up. But that pure acetic acid, I mean, it may be a weak acid, but if you stick your hand in a jar of that stuff, it'll eat it off. So the acidity and the equilibrium constant are two different concepts. All right. The other thing about these organic acids is you don't want to store them with oxidizing acids or oxidizers of any kind because they're organic. You put them together with an oxidizer, you get an exothermic reaction and it can make a mess.
So like I can. And so I think we have to use 5% vinegar for canning or it gets rancid. So why is that? And so because like Walmart was selling 3.5% vinegar and everybody was on Facebook like, don't get this because you have to use 5%.
Right.
So why do we have to use 5% instead of 3.5?
It's the preservative effect. Most microorganisms, there are a few that can exist in acidic solutions, but most of them don't like acid environments. So even with 5% acetic acid, you get enough hydrogen ions or hydronium ions in there that disrupt the growth cycle of microorganisms. But if you use a weaker acid, then it's not acidic enough, and those microorganisms will proliferate.
So it goes rancid essentially.
Well, yeah.
Okay.
Well, rancidity is kind of a general term. Rancidity can also mean oxidation of fatty acids.
Yeah.
I think that happens to like nuts that you keep in the pantry for too long. They go rancid.
What do you keep in the pantry?
Like walnuts, pecans.
Oh, okay. Nuts.
Nuts.
Okay, I couldn't understand
I
what you
think said
said.
gnats.
Yeah, I did too.
Mouthful.
Okay. Yeah, there are a whole host of reactions that can go on. See, the thing about studying chemistry is we start off with general chemistry and we keep things really simple. Like this reacts with this in that environment. But in the real world, you've got a big soup of reactions going on. So eventually that's where we're headed. I mean, if you're a synthetic organic chemist, then you can control the environment so you can get the product you want. But in the real world, in the biological world, those reactions are like just a big soup. And the way your cells control them is with enzymes. Because most of them won't react to a considerable amount unless you have some type of catalyst. So that's where the enzymes come in and they control the reactions. And the DNA and RNA control the enzymes. That's another topic. Okay. Le Chatelier's principle. We haven't covered that either. Okay. So what we mean by Le Chatelier was a French scientist. And what he observed was, if you have an equation that's at equilibrium, let's say we have an A plus a B is in equilibrium with products like that. If that's in equilibrium and you have a certain concentration of this, this, and this, and this, so that they're going equal rates like that, Le Chatelier described what the system will do if you disturb that equilibrium, if you take it out of balance. The easiest way to do it is either add a reactant, add a product, or remove a reactant, or remove a product. Change the concentration. If you add A, now you're going to have more A to react with B, and the rate's going to increase in that direction until you get enough of this so that the reverse rate catches up with it. Okay, that's what Le Chatelier is saying. Now, there are other ways to affect the reaction rate. You can affect it with temperature. If the reaction is endothermic or endothermic, that'll determine whether it goes one way or the other. When you say increase the temperature, and when I do that, I put the heat as a term. Enthalpy. If it's exothermic, then the heat's generated as a product. And if you increase the temperature, you're increasing that factor, and it drives the reaction this way. Okay. If you have gases involved, like you have gases, if each or even just one of them is a gas, then what you look at is the coefficients. What's the stoichiometry of the reaction, right? Is this one 2 and that one's 3, and this one's 1 and this one's 2. So the total moles of gas on this side is 3 and the total on this side is 5. So the response of the system is, if you increase the pressure by decreasing the volume, right? Boyle's law. We squeeze it, then it's going to try to produce fewer moles of gas to relieve that pressure. So if you squeeze it, it's going this direction. If you expand it, then it's going to go back the other direction. If the number of moles is the same on both sides, it doesn't matter what you do. It's not going to change. Squeeze or expand. Okay, that's Le Chatelier's principle. You might even be able to skip those lectures.
Probably not.
Okay, so here's our calculation of pH, right? We already covered that. It's Sorensen's transformation. The percent ionization, or Carty calls it ionization states. And the dominant ionization state depends on the solution's pH. Okay, so now we're using the concept of what's the pH and what's the pKa to determine what are our dominant species. Because if you know what your dominant species in a particular reaction are, then you have a better handle on what type of reaction you're going to get. Right? Do you have a fully protonated reactant, or is it deprotonated? That makes a difference in what reaction is going to take place. All right, so let's see. All right, here's an expression of the KEQ. Now this KEQ is a general K for any reaction in equilibrium. And what we haven't said here is anything about which terms do you drop out. If you have any term has an S next to it, right, it's a solid, that drops out of the expression. If you have an L next to it, it's a pure liquid, that drops out. The reason being, solids and liquids don't change concentration. Only gases and solutions. It could be aqueous solution. In organic chemistry, it may be non-aqueous solution. But if it's in a solution or it's a gas, then it stays in the expression. But if it's a solid or a liquid, it drops out. And the value of KEQ, we never report values. We never report units. Because you have so many different concentrations and you have different powers based upon the coefficients, that the units of measure would be a nightmare to track. So we're just real careful about when we calculate a KEQ, and we don't put units assigned to it.
That's a lot to take in.
Yeah, if you haven't had it in general chemistry yet, yeah.
Yeah.
Good for you that like you're.
We're going to get to it. Let's see.
I think next week.
Yeah, we have an exam coming up, right, on
Tomorrow.
kinetics. And then next week, we'll introduce equilibrium.
And then we have the Le Chatelier lab, so.
Yeah.
That's next week, yeah.
It'll make a whole lot more sense after
Yeah.
that, I think. The Chatelier lab is fun because it's not a formal report.
Yeah.
Okay. So when we have a very large K value, that favors the reaction moving toward products because of the way the expression is written. If we have a very small K, the reactants are favored. If the K is close to 1, we can't say it's exactly the 1 because of the way that the expression is written. But if it's close to 1, then you're pretty much balanced reactants and products. Okay, so here's an expression for Ka, and that's an expression of acidity. Notice that in this expression, the liquid water is not in the final expression. It dropped out. So we only have the acid in the denominator, and we have the conjugate base and the hydronium ion in the numerator. And notice the subscript is Ka. So the K means an equilibrium constant, but the subscript gives you a clue as to how it was derived. The Kas are all acid dissociation constants. Okay. KEQ is just a generalized. There are other types of Ks. KW for water, right, is special for water. KW means hydrogen ions times hydroxyls equals 10 to the minus 14. That's it. Okay, there's our expression for conversion of pKa to Ka to pKa. It's just Sorensen's transformation, negative log of Ka. All right, I'll throw this one at you. If you want to know, if you have a buffer, buffers are usually formed, not always, but usually formed from a weak acid in combination with its conjugate base. So if we have the acid here, right, and it's in equilibrium with its conjugate base, And these concentrations, if you have some of this and some of that, then you can have a buffer.
Depending on the amounts.
Yes. The ideal buffer is equal amounts. And the Henderson-Hasselbalch equation is a derivation of the Ka expression. So if you say, what would be the Ka for this? Like we have that. So we would have the Ka here is equal to hydrogen ions and the conjugate base divided by the acid concentration. Okay. Now what Henderson did, Henderson was interested in the expression of wanted to know what the hydrogen ion concentration was. So Henderson came along before Sorensen did his negative log transformation. So Henderson just solved this equation for HA. So the hydrogen ion concentration is equal to Ka times HA over conjugate base. That's Henderson's contribution. Then Sorensen came along and introduced pH and pKa. So Hasselbalch took this and he transformed the entire equation with a negative log. He just said negative log here and negative log here for that whole thing, and then resolved it. So the negative log of this one is pH. The negative log of that one is pKa. Right. So what happens when you take the log of A times B? It's the same as the log of A plus the log of B. Remember that from math?
Maybe. I never took any math that used log. I don't
Really?
know.
Oh.
So whenever I had to do this in chemistry, I was like, what the heck? But then it's not that.
You had to learn it. Yeah. Okay, so this gives us pKa here. And this gives us, actually, Hasselbalch knew better than to try to convert this into PHA and PA minus. So he just said negative log of this ratio. Okay? But we don't like to have negatives sitting anywhere because it's too easy to make a mistake. So if everything can be positive, we're good to go. So how do you make a positive log out of that one?
Was it the inverse of it?
You invert this part of the equation, and that makes it positive. So the conjugate base over the acid is positive now, and pKa equals pH. Okay. So here's where the ratio of the conjugate base to the acid comes in. If you have a weak acid, so this pKa is 4, 5, 6, 7, or 8, something like that. Right? It's not really small. It's not 1 or 2. It doesn't work as well for those. But if you have something like acetic acid, 4.75. If you want to know the pH of the solution, you need to know the pKa of the weak acid, and you need to know the concentration of the conjugate base and the undissociated acid. If you know those three factors, then you can calculate the pH of your solution. Notice that if you have equal concentrations here of these two, right, that gives you this divided by that is 1, right? What's the log of 1? 10 to what power is 1? 0. 10 to the 0 power is 1. So that becomes 0, and pH equals pKa if these are equal. Okay. Now, if we do a titration of a weak acid with a strong base, you can get a titration curve, and you can find out where that buffer zone is. What's a buffer in acid-base terms? it's a mixture of a weak acid with its conjugate base that resists the change of pH if you add an acid or a base to it. Right? If you add an acid, the acid is Le Chatelier takes over and consumes some of that acid. So it keeps it from changing the pH, lowering the pH. If you add a base to it, it also consumes the base to keep the pH from rising. I mean, it's not fixed, it's not a constant value, but it keeps it from moving. That's what a buffer does. So this final equation here, pH equals pKa plus log of conjugate base over acid, is the Henderson-Hasselbalch equation. So if you have 50% dissociation of your acid, then you get an equal amount of this and an equal amount of that, and your pH equals your pKa. Okay. For a proton transfer reaction, we can calculate the KEQ if we know the change, the difference in pKa. So if we have a difference in pKa of the acid on the reactant side and the conjugate acid of the base on the product side, then all you have to do is, what's the difference between the two? And then 10 to that power is the KEQ of that reaction. Okay. This is discussed in your book, I know. So check it out in the book. Maybe he explains it better than I am. All right. So my first semester students, general chemistry students, get this Gibbs free energy discussion. Remember Gibbs free energy? We talk about entropy, free energy, total
That was like the last.
internal energy.
What we got into in 160 with
Yeah.
like S.
Uh-huh. Yeah.
All of that.
Entropy.
I don't remember all.
You remember
Like like the
Gibbs equation?
Yeah.
Remember that?
we
Okay.
had an equation sheet where we got some of that.
Yeah, on our exams, we got equation sheets,
Okay.
but we had to like know what they used. And it didn't like, it
Right.
wasn't like the equation with the question. It was like, here's a bunch of equations, now know which one to use.
Right. I do that with my general chemistry
Yeah.
class. It doesn't seem to work as well in this class.
No.
That's- we're not
Equations.
right. It's not heavy equation driven.
The IHD stuff, that was tricky. I had to remember how to.
Oh,
calculate
yeah.
That's kind of an equation.
Yeah. Yeah, it is. Mhm. Okay. So the reaction is favored in the case where the Gibbs free energy is a negative value. If delta G is calculated to be negative, then that is favored. Right, remember that discussion where you compare the enthalpy of the reaction and the entropy of the reaction, the temperature is a variable. So if it's endothermic, right? And it's the delta S is also positive. And how do you get a negative out of that? In order to get a negative out of that, temperature has to be very high to make this negative bigger than that one. So you only have a spontaneous reaction for this situation when the temperature is extremely high. If we reversed it and made these both negative, right? The only way you can get a negative sum out of this is to make the temperature very low. So that makes this positive. Negative times negative makes this positive very small. And that still gives you a negative. So under exothermic reactions, then you would need a low temperature. Okay. That's the problem that Haber faced when he was trying to make ammonia out of nitrogen from the air. It's an exothermic reaction, but he knew he needed a high enough temperature for the reaction to go, right? Because he knew what the activation energy was. But since it's exothermic, then a high temperature would not favor a negative delta G. So he got around that by introducing a catalyst and very, very high pressure, like 400 or 500 atmospheres.
Have you guys done some catalysts yet?
Um,
I mean, there's not.
we
There's
talked
not
about them,
lot
yes.
That goes into it, it just.
Yeah.
But it's not.
Yeah, and the kinetics, we talked about catalysts. Right. Well, I digress. Let me get back to the topic here. A reaction is product favored if delta G is less than 0. So if this is negative, then it's going to favor the forward direction toward products. And if it's positive, it's going to favor the reactants. The terminology there is exergonic is delta G minus, like exothermic is delta H minus, and endergonic is delta G plus, similar to delta H plus is endothermic. Okay. But when we're talking about this, we use erg rather than therm. So here's a free energy diagram. If the reactants are higher G, right, a delta G would be subtracting the two. If the reactants are a higher G than the products, then you get a product minus reactant, lower value, minus the higher value. Right, which would make it negative. Right. So for the one on the left, the G of products is smaller than the G for reactants. So this is a bigger value, makes that overall value negative, delta G. So the one on the left favors products. And the one on the right favors reactants. The trace, the diagram, the free energy diagram. Okay. So we go back to this one where delta G negative means the forward reaction is favored. If the delta G is positive, the reverse reaction is favored. All right. We can also take the delta G for the overall delta G for the reaction, and we can use that to calculate the equilibrium constant. Right? The delta G for the reaction equals negative RT times the natural log of K. And there he's also pulled out Gibbs' free energy equation that right here. It's the same thing, that second equation. I think he's going to combine them. So if delta H is greater than 0, then the reaction absorbs heat, right? Well, we know that already. If it's less than 0, it's exothermic, right? So what does that mean in terms of bonds? If you break a bond, you've got to put energy into it to break a bond, right? Yeah. You got to increase the energy so much that the bond breaks. If a bond forms, then it gives up energy because the bond tends to be a lower energy state than the free atoms. All right. The entropy difference, the delta S, is an expression of the change in entropy from reactants to products. So if in general, now this is an oversimplification, right? But in general, A reaction in which the number of separate species increases has a delta S for the reaction greater than 0. Okay, if you increase the numbers of moles of product overall, then you're increasing your entropy. You're increasing disorder. The proper term is you're increasing the number of possible microstates. If that were
I never got my macro statement.
okay.
I didn't get that.
It's statistical. Yeah. So we're gonna keep it really simple. We're gonna think of order and disorder. Fewer means more ordered, more means less ordered. Increase in entropy is more stuff. So if you break a ring, you're increasing the entropy. Okay. Let's see. The acidity of a compound is mostly governed by the functional groups on which the acid proton is found. So ethanol, which has a pKa of 16, is slightly more acidic than propane-2-ol. That's also known as isopropanol. Okay. To look the way I drew it earlier, just take that molecule and rotate it to put the OH on top. And that puts the OH on the second carbon. That's isopropanol. Both molecules are alcohols, but the ethanol is slightly more acidic than the isopropanol. They are similar, though. Very similar. Now, if we have molecules that are radically different from one another, like acetic acid, right? It has that carboxylic acid group on the end versus the carboxylic group on a benzoic, on a benzyl group, then those have more divergent pKs. And remember the effective electronegativity. Remember that concept? The more pi bonding you have, the more effective electronegativity those carbons have. So these carbons right here would have a lower effective electronegativity than those carbons attached to anything else. All right, so the higher electronegativity tends to draw electron density away from whatever's over here. And if you've got something else over here with, say, a hydrogen on the end of it, then it's going to tend to pull electrons away from that hydrogen and make it more acidic. So that's why the benzoic acid is slightly lower pKa, because of those double bonds attached to it. Cyclohexanone, what are we trying to do here? Using table 6.1, estimate the pKa value for the indicated CH2 protons. Okay. All right, I'm going to have to let him solve this problem for us because I'm not getting what he means there. Okay, on what functional group do the acid protons appear? All right, so A appears on a carbon and B appears on a carbon. The difference is that the A carbon is also attached to a carbon that's attached to a carbonyl, which means it has the effect to draw away more electron density from that carbon and makes the A hydrogens more acidic than the B hydrogens. So we should see a lower pKa for the A than we do for the B. I know that much. All right. Let's see. Well, that's a cycloketone actually. Let's see. The pKa of acetone, another ketone, is 20. We should expect the pKa for the proton A to be about 20. Actually, it won't be exactly that. It'll be close, though. For protons B, the pKa should be similar to that of alkane because it's not part of that functional group. So alkanes, methane is 48, ethane is 50. So it should be somewhere between 48 and 50 for the B and around 20 for the A. All right, so we're generalizing. How are we doing on time?
11:50.
Okay. I wanted to give us an hour and a half for the lab. How many more slides do I have?
Quite a few.
Yeah. Okay,
We're not even halfway through. Well, yeah, we are.
maybe halfway.
Yeah, because we have 73 slides. And we're on slide 39.
Okay, this is a general rule. A proton is dramatically more acidic when it's attached to a positively charged atom than when the atom is uncharged. So if we have, remember the carbocation thing? If we have like this, and say we have a terminal like that. Carbocation, if we put a carbocation there, that makes this more acidic. That hydrogen wants to leave more because we're drawing electron density away from. If this carbocation is within 2 carbons of that oxygen, then it will have a, oh, I forget the term. It will draw electron density away. Okay, make it more acidic. That's all we're saying there. The positive ions tend to be more acidic. Okay. This is an explanation for it. Autoionization of water. All right. Well, the autoionization of water is not favored, right? Because the free energy goes up for the product side, right? So this is not favored, this reaction. It happens, but it's not favored. The reactant side is favored. That's why the Ka is so large. So small, excuse me, 10 to the minus 14. So how do we keep track of these formation of charges? Well, you can go in and calculate the formal charge de novo, as they say, just out of the blue. Or you can start from neutrality and you can say what electrons are moving where. Let's take this ammonia, for example. We have this one here, here, like that, like that, like that. What's the formal charge on nitrogen? It has how many valence electrons? 5, isn't it?
Mm-hmm.
It's 5. Okay. So it's assigned 1, 2, 3, 4, 5. Minus 5 is 0. So this starts out at a formal charge of 0. Right?
So you're counting part of the 5 as the double.
Yeah. I
Double
count
bonds?
1 from each bond. 3 plus these belong
Okay.
to nitrogen.
So you count those as 2 up there.
Yes.
Not just 1. Okay.
Right. Now, if we break a bond, which is, and produce this molecule, that, and we remove, say we, let's see. Yeah, we have the water molecule with these, and we say, what we're going to do is we're going to form a bond with that hydrogen, and then these 2 electrons go up here. So now they're down here.
So
Okay.
that would be 6, correct?
Right. If we go ahead and
Oh, okay.
if we calculate it now, 5 minus 1, 2, 3, 4, 5, 6, we have -1 charge. That's the long way to do it. The quick way to do it is to say, all right, this nitrogen is neutral, right? Has a formal charge of 0. If we break that bond, then one of those electrons was already assigned to nitrogen to make that neutral, that 0 formal charge. But now we've got this extra electron over here from that bond. It's going into here. That makes it -1. So we can figure those charges quickly. by watching how the electrons move. Okay. So what are the effects of additional charges in energy diagram? Well, let's see. If we go from the ammonia to make the H2N minus, the deprotonation of H3N is energetically less favorable. That's why that red is such a high, it's a high barrier to exceed. But if we've got the ammonium ion, then it tends to lose that proton more readily to water. And its energy barrier is much lower. So the blue one is favored and the red one is not. Well, the blue one is more favored. It's not particularly favored, but it's more favored than the NH3 deprotonation. Okay. How do we explain the relative acidity of species bearing the same charge? Okay, all these factors have to be considered to determine the acidity of protons. What is the identity of the atom they're attached to? Are they attached to sulfur? Are they attached to oxygen? Or are they attached to carbon? What are they attached to? Are they attached to a halogen? What's the hybridization of the atom? Right, so the hydrogen is attached. The hydrogen is not going to hybridize. It only has a 1s orbital and that's it. It's not going to do anything with it. Right? So what's the hybridization of the atom it's attached to? And then are there any nearby pi bonds? Because they will increase the effective electronegativity of any atom attached to them, which is usually carbon. And then any other nearby atoms within, if there's a highly electronegative atom within two atoms of your hydrogen or two carbons of your hydrogen, then it's going to have an effect. If it's attached to one away, it's going to have a huge effect. So the example I can think of is the Grignard reagent. Say if we have this one and maybe this one, I think it's two. Then we have a magnesium and maybe a chlorine. Right, so the attachment of those atoms, the nearby atoms, tend to activate this carbon with its hydrogens. Okay. It draws the electron density away and tends to give this slightly positive charge, which makes it electron deficient. So if you have another reactant over here that has maybe a lone pair attached to it, I better not use X because that means halogen, a carbon of some kind, then this is going to attack that deficient carbon. And when it does, it forms a bond. So Grignard reagents are generally used to form carbon-carbon bonds. That's one of the reactants I remember. There are a whole lot of them that I don't remember. So that nearby atom activates the carbon. Okay, protons on different atoms in the same row of the periodic table. All right, so if we go from protons attached to carbon, so if the protons are attached to carbon, nitrogen, oxygen, fluorine from left to right, then the increasing electronegativity from left to right of carbon versus nitrogen versus oxygen versus fluorine determines whether you have a more stable anion. The more electronegative, the more stable. So the anion of methane, which would be CH3 minus, right, loses a hydrogen and makes a CH3 minus, is less stable than the NH2 minus. And that's less stable than the OH minus. So this concept of stability of products is essential be reactants too. The stability of any of these species is essential to understand which ones actually enter into the reaction. If the product is stabilized, then the reaction that you propose, the mechanism you propose, is favored. Or if the reactant is stabilized in a certain form, then that means it's ready to react with something. I mean, it's not flipping around. It forms a species that is reactive if it's stable. And this also speaks to the concept of leaving groups. In other words, if you've got a reaction that needs to get rid of something as part of the process, right, to make the product, then the more stable the leaving group, the more likely it is to go. We'll get to that in more detail later, but I thought I'd throw that in for free. All right. Uncharged acids. In this process, the bottom one, the red one, the NH3 is a stronger acid than CH4, so the deprotonation is more favorable. Right? Methane is not a strong acid, and all you have to do is compare the pKa's. So the pKa of methane should be fairly large. Let's see, methane. Here it is, 48. The pKa of methane is 48. What's the pKa of ammonia? Okay, ammonia is 36. So this is ammonia, and this is methane. So the energy change for the loss of a proton here is smaller. It's more favorable than that one. So if you look at the products, the stability, if this loses a proton, then what do you have? You have CH3 minus. If you lose a proton here, it's NH2 minus. So this one is more stable than that one, because this one wants to lose a proton more than this one does, and it produces a more stable anion. And that is shown in the red trace. And then if you take a series in the same period, the anions that are formed from the neutral compounds of hydrogen from left to right becomes more stable as you go toward fluorine. So OH minus is more stable than NH2 minus, which is more stable than CH3 minus. All right. All right. So what I see here is the hydronium ion is compared to the ammonium ion. So the ammonium ion is a larger energy change from its charged state to its neutral state. You know what? Okay. They were confusing there for a minute. They got the lines starting blue and red, and then when you get to the product side, they flip the ammonia on top and the water on the bottom. See that confused me. Okay, so the change to ammonium, actually they end up in the same place, but what's the difference? The change in free energy. It's a larger change in free energy to go from ammonium to the uncharged ammonia than it is from the hydronium to the uncharged. So the hydronium is favored, right? It has a smaller energy change than the ammonium does. All right. I'm not doing too well with these, so I'm going to skip those. That looks like the same as before. Okay. Protons attached to different atoms. We mentioned those factors. So attachment to atoms depends upon the electronegativity of the atom. The stability of the anion tends to increase when the negative charge is spread over a larger volume. So that means the chloride ion should be more stable than the fluoride ion, right? It's a single charge, but it's spread over a larger area. That's more stable. So the chloride is more stable than the fluoride. All right. How does hybridization affect? Well, that goes back to effective electronegativity. Oh, we didn't even talk about that yet. I was using those terms and we haven't defined them yet, correct? Right. Okay. So the number of double bonds is correlated with the hybridization of the carbon atoms. If you have a single bond only between two carbons, then the carbon is sp3 hybridized. It has a certain electronegativity. If it's sp2 hybridized, then you have an increased effective electronegativity of that carbon. And the reason for that is the negative ion, the negative charge on the sp2 hybridized carbon is more stable. And the sp hybridized is even more stable than that. So the stability of the charge relates to its effective electronegativity. All right, so we have this comparison of acetic acid and ethanol. There are resonance effects also. In other words, ethanoic acid has the ability to resonate with that double bond. I think they're going to show it on the next page. So ethanoic acid is a stronger acid than ethanol because the resonant forms help to stabilize it. So let's see, here we go. Okay, so what happens when you lose a proton from ethanoic acid? You get the possibility of forming that negative on one of the oxygens, but you can just as easily put the negative on the other oxygen. So how would that look in terms of arrow pushing? We have this carbon, we have the carbonyl here, we have the O here and the minus, and then we have our methyl group. Okay, if we put in all of our lone pairs, right? 1, 2, 3, 4, 5, 6. Then what we can do is we can let's see, which way are the electrons going to move? Electron rich to electron poor. So if we do this, right, move those two electrons up here, then these two electrons have to move down here. Otherwise, we'll exceed the octet. 2, 4, 6, 8 already. So if these move up here, then those two have to move down here. And that gives us resonance with this one. Okay. And resonance tends to stabilize the ion. So this is more stable than the than the ethanol possibility. So we have ethanol here, we have CH2OH, and if we lose that, we get negative there. It can't resonate with anything, right? So it's less stable. That's why this is more acidic than that one. That's known as the ethoxide anion. All right, this is a way of looking at it. I'm not going to spend a lot of time on this. We can get a similar effect from the hydrogen sulfate anion. After it loses a hydrogen, it produces the HSO4 minus anion, and the resonance stabilization delocalizes electrons and makes that more stable. So the first proton that leaves H2SO4, the first proton that leaves it, leaves us with this anion. And this is more stable because of its resonant ability. But if we try to take another proton away from it, it doesn't like it. It's not as easily stabilized. Okay, ethoxide versus 2-chloroethoxide. Now what we're doing is we're inducing stability with an attached electronegative atom. So if we go from ethoxide and we replace one of those hydrogens on the methyl group with a chlorine, then it tends to let's see. You have a high concentration with the ethoxide ion of negative charges on that oxygen. Okay, if we add chlorine, it draws some of that electron density away from the oxygen side by inductive effects. And that stabilizes the ion because now you don't have that high concentration of negatives on that oxygen. You've drawn some of that density away from it. Delocalize the electrons by putting that chloride in there, or that chlorine in there. So the 2-chloroethoxide ion is more stable. That means that the 2-chloroethane is a stronger acid than 2-chloroethanol is a stronger acid than ethanol. Okay? Yeah. And this is illustration of the inductive effect. Let's see. We can see an inductive effect in cations as well. Right? If you do have a cation and you have an electronegative atom within 2 carbons of it, then it tends to destabilize because now it's drawing more electron density away from that positive charge and separating charges more rather than dispersing the charge over the electron density over the group. It tends to concentrate on one side, so it has the opposite effect on the positive ions. It has a destabilizing effect. All right. So what do we mean by electron donating groups? Well, one such donating group is any alkyl group. It can donate. It's slightly polar toward the carbon. So that makes the carbon a little slightly negative, and it gives it that ability to donate some of those electrons into whoever, right? The effect of that is if we replace those hydrogens with methyl groups, then when we form the anion, rather than the I forget the name. Then give me the name. The amine anion. And replace those hydrogens with methyl groups, they donate electrons to that negative and destabilize it. Right, so it's less likely to form the anion for the methyl substituted than it is for the amine group. However, if you have if you start off with an ammonium ion, and you replace one of those hydrogens with a methyl group, now the methyl group is a donator, and it stabilizes that positive charge. So the monoamine methyl cation is stabilized rather than destabilized. It tends to stabilize the positive group. So there's your summary of inductive effects. I'm not going to sit around for that one. So here's this rule is talked about in your textbook. Right? So what does it mean? Well, this is priorities. The cardinal rule is priorities. Which ones have the greatest effect on stabilizing a charged species? Priority for charge stability factors. Okay. So I don't know why they put the charge in there, I think, just so that the acronym would fit. I mean, ordinal doesn't mean the same thing as cardinal, right? So you put this charge in there. All right. So the charge, oh no, it does have a greater effect, right? If you have a charged species, then you're looking at either a stabilizing or a destabilizing effect. So the charge has its greatest effect. Then the atoms attached to it have the next greatest effect. If you can resonate and delocalize the charge, then that has an effect, but it's lesser than the atom and the charge, and the inductive effects are last. Okay. All right. So I think this is illustrating the cardinal rule. The difference between charge. So we're the ammonium versus the ammonia. Right, that has a much greater effect. The pKa difference here is 26. Right, the atom type. Say we have water versus ammonia. The difference there is only 22. So it's not as great an effect. Or the acetylene versus the ethane is a lesser effect than the charge. Resonance, right? We've already seen that effect. It's significant though. I mean, it's a difference of 11 in pKa. So the stabilization there is different. And the inductive effects are even smaller. All right. How much more do we have? A lot.
22.
22 more?
No. 1, 2, 3, 4, 5, 6, 7, 8. 8 slides.
8. Oh, okay. So maybe that'll give us an hour. So can we rank the strengths of these 4 acids based upon the cardinal rule?
Yes.
Okay. So we have this, and they're similar, right? They have 1 fluorine. Now that one has a fluorine. This has alcohol groups, and this one has a functional carboxylic acid group. And this one is a protonated hydroxyl. All right. So what we look at in terms of stability is form the ion with reaction with water. So we do that with each one. And what do we get as a consequence? Well, charge stability should have an influence that will give us the red one, I think, should be the most stable one. Right? Is that true? Yeah, the red's most stable. Uncharged conjugate base is more stable. And then the next most stable is the one that forms the carboxylic acid.
For the purple one.
Let's see, is that the right? Yeah, that's kind of a blue. It's a dark blue rather than a light blue. Okay. The next most stable is the alcohol with the fluorine. The fluorine is on a secondary carbon, and the fluorine in the top one is on the primary carbon. Right. So the strength of the acid is ABDC. Okay. So A goes up to here. That's the weakest acid. So oh, I see the order they're putting them in. The strongest is C. Right. Okay. So the charge effect there gives us the strongest acid here is C. Then D is a more stable form. So that's the next strongest acid. That's resonance effect. And B is weaker, but it's stronger than A because it has the effect of fluorine within 2 carbons of the hydroxyl. And this one is the least acidic because the fluorine is way, way, way far away. That's the way I take that. Okay. Here's an amino acid, right? I think I mentioned amino acid before, didn't I?
Yeah.
You have the alpha carbon. And then you have, here you have the amine group. Right? And that's got a lone pair on it. And here you have the acid carbon group. Right? This has 2 lone pairs. And then over here you have the R of something. Anything over here is permitted to complete the amino acid. Now, the form that it can take depends on the environment. What's the pH of its environment? And it also depends on what's the pKa of this group and what's the pKa of that group, because they will act independently of each other. Okay. The pKa for this one right here is about 2. pKa of about 2. The pKa of this one is about 9, 9 or 10. 9 to 10. Okay. So, before we talk about what happens when, what can happen is this can become protonated and this can become deprotonated. So we can have this, let's see, they're drawing it with just lines. So we can go like, let's see, go to that carbon, and then we can go here, here, and then we can go to this one, in H, and then we can go to this group over here. So what can happen is this one can be protonated, which would be what? It would make it a positive charge. Because we had a lone pair here, and now we're taking that lone pair to combine it with a hydrogen to make that bond. So we've actually removed 1 electron from that nitrogen makes the group positive. And then this hydrogen's missing, and now that makes that negative. This is called a Zwitter ion. That's German, I think. Zwitter ion means both ions on the same molecule. So it doesn't happen this way, but you can think of it in terms of that hydrogen being transferred up here. What actually happens is it goes to some intermediate, right? And then it's transferred. Usually water. It uses water as an intermediate. And it depends on the pH as to whether you have the Zwitter ion formed. So if the pH is less than 2, that means we have an excess of hydrogens in the environment, right? If the pH is less than 2, got all these hydrogen floating around. So this hydrogen is going to attach there and leave that one positive. So the ion form here is this one is protonated and that one's protonated. So high pH means both functional groups are protonated. If it's somewhere between 2 and 9, then you get this one. 2 to 9 pH is you get that form, where you have this one is neutral and that one's neutral. If you go greater than 9, then you get, let's see, greater than 9. Now you deprotonate this one and you leave that one negative. Because this one is more likely to give up its hydrogen ion. This is the stronger acid side than that one. So if the pH is greater than 9, that means it's a basic solution and there are lots of proton acceptors out there. And they're going to accept that proton really easily, but not so much this one. So that's what your ions look like, depending on the pH. And this is fairly common for the amino acid part of the molecule. Now, some of them have acid or base functions out here on the R. So you can get that as a complicating factor also. All right. Let's see. I'm going to skip that because we don't have a lot of time. There's one where lysine also has a functional group out here on the R. Right. So that ammonia, right? You've got a 2 and a 9 region for the amino acid part of the molecule, but you also have this other amino group out here, which is in the same region as the amine group next to the alpha carbon. So it's going to behave similarly. Right. So if the amine group here is protonated, the lysine amine group at the end is also going to be protonated. All right. That's enough of that foolishness. Now, let's do some lab.